Let's look now at the different components of the blanket. First, the first wall design. The first wall is subjected to normal and off-normal heat fluxes from the plasma. Just to simplify a little bit, this just gives a schematic of the first wall from first wall 1 to 18, blanket module 1 to 18. It has to handle steady state heat fluxes from the plasma when the plasma is radiating. So all the radiation from the plasma needs to be accommodated by the first wall 1 to 18. When you start up the plasma, typically on the inboard on first wall 3, 4, 5, or when you ramp down, could be on the inboard or on the outboard from 14, 15, 16, or 17. Typically, the heat fluxes there tend to be higher. So the blanket has to be designed, the first wall there has to be designed to handle this. And on top of that, sometimes you have disruption of the plasma due to instabilities. And before the plasma is quenched and dies, if you want, you have a lot of energy which is liberated and which is deposited on the first wall. And this creates also quite a design challenge. So how do we deal with these different high heat fluxes to the first wall? So we use shaping of the first wall panels. So the heat load associated with the charged particles in the plasma represent the main component of heat flux to the first wall during operation. And this heat flux is oriented along the magnetic field lines. It follows the field lines around the torus. So this incident heat flux then is strongly design dependent. Depends on the incidence angle between the field line and the component surface, the first wall surface. Now, in the first wall, we have leading edges because one first wall is separated by the other. You have a gap and a leading edge. We have a slot in the middle of the first wall to accommodate remote handling. So we need to protect or shadow these leading edges at the gap between the two first walls or for the slot. And this is why we use shaping. On the bottom left, you can see an exaggerated first wall shaping, which gives you a better idea. You can see the magnetic field lines, which basically hit the first wall, but the remote handling access, the slot, is protected. The particle fluxes which follow magnetic field lines will not impact the slot area. So this allows good access for remote handling and the shadowing of all leading edges. So that's why we adopt first wall shaping. Because then of a different distribution of heat fluxes in the first wall, we have two different kinds of first wall panel configuration. We have the so-called normal heat flux, which are designed for 2 megawatt per meter square. And we have enhanced heat flux panels, which are designed for 4.7 megawatt per meter square. These EHF panels, designed for 4.7 megawatt per meter square, typically have the inboard to start up the plasma, first wall 3, 4, 5, and at the outboard for ramp down, 14, 15, 16, 17, and in the top region, 7, 8, 9, where you have a secondary X point and where the heat fluxes is higher. All the other first wall panels are designed for 2 megawatt per meter square, the so-called normal heat flux. Just to give you an idea what this means in terms of heat fluxes, if you, on a summer sunny day on the beach, the heat flux from the sun is about 0.001 megawatt per meter square. We are designing from 2 to 5 roughly megawatt per meter square. Even the space shuttle, I'm sure you must have seen pictures of a space shuttle before, where you have a number of tiles at the bottom, basically to accommodate the friction heat for the shuttle re-entering the Earth atmosphere. And the heat flux of the shuttle sees there is 0.5 megawatt per meter square, which is about a tenth of the heat flux that some of the first wall panel will see, just to give you an idea as a comparison. So how do we design the first wall design? How do we design the first wall? The normal heat flux, which is being procured by the EUDA, uses a fairly conventional design in a sense, at least in terms of configuration, where you have a barium tiles, and then just behind it you have a copper chromium zirc alloy as a heat sink, in the middle of which you have cooling channel, the plasma side, I would say cooling channels. At the back in blue, in dark blue, you have the structural material, the stainless steel 316, with also a bigger channel there. So typically, if you look at the figure just on top of it, the coolant will come in, will cool the first wall plasma side, and then we'll come back and cool the back, the larger channel of back, and then we'll exit. For the enhanced heat flux, which is being procured by the Russian DA and the Chinese DA, it has to be designed for a higher heat flux. So we need a special design, which we call a hypervapotron, which basically, shown is orange there, are a bunch of teeth along the channel. And with these teeth along the channel, this helps the heat transfer to be much better than in a conventional design. Okay, so we use this hypervapotron design, and then we use different techniques in order to bond the material together. I don't want to get too much detail there, but basically, in both cases, heaping, hot isotopic pressing would be used, and also brazing would be used for the beryllium to copper-chromium zirconium bond. Now let's look at what we call off-normal events. So when the plasma is operating, sometimes you can have global instability, which will terminate the plasma. And this could be triggered by plant malfunction or some other plasma instabilities. So basically, the plasma energy and the current decreases very fast once you have such a disruption, because you lose vertical position control, and these result in huge power fluxes to the plasma-facing components, plus also forces because of the current, the product of current and magnetic field results in force. So this affects the vacuum vessel and also all in-vessel components, including the blanket. And you can see that typically the plasma current quench occurs over the order of 100 milliseconds, whereas the thermal quench is much quicker. It occurs over 1 to 10 milliseconds. And what does it mean then? If you look at the figure on the top, the graph on the top with a yellow background, this shows the temperature of the armor following such a high energy deposition. You can see that it goes past 2000 degrees, much higher than the melting point of beryllium. So you're going to melt and evaporate beryllium. On the right there, you can see the melt layer thickness up to about 1 millimeter. So the strategy then is to make sure that we have only a few such disruption, and that we can use a disruption mitigation system to mitigate the effect of disruption by injecting a pellet inside when the disruption is about to occur. And then this will reduce the heat flux to the first wall, and the first wall will be able to accommodate many more of these mitigated disruption. You can see at the bottom a typical example where the temperature for a mitigated disruption is much lower. Actually, in this case, you don't even melt the beryllium, but you do evaporate a little bit, but really a very small fraction. So the strategy then is to set the beryllium armor thickness as thick as possible within the constraint of maintaining the maximum beryllium temperature to 600 degrees C in general, or 800 degrees C in some local zones. And this resulted in choosing an armor thickness of 8 to 10 millimeter, 8 millimeter for the EHF first wall and 10 for the NHF first wall. And you can see then that this can give you only the possibility of accommodating a few non-mitigated disruption if you're going to use of the order 1 millimeter each time. Now we look at the shield block and blanket module connections at the back. So this is an example shield block, which is shield block number 4. You can see on the front of the shield block there are a number of slits, and these slits are included for two reasons. One is to reduce the EM loads. When you put the slits, then the eddy current loops are much smaller. This reduces the current, and when the current crosses the magnetic field to produce the forces, it reduces the forces also and the stresses on the material, on the component. And it also minimizes thermal expansion and bowing. Inside the shield block, cooling holes are designed to provide the required thermal hydraulic performance while aiming for a water to stainless steel ratio, which will result in good nuclear shielding performance. You can see on the graph, in the graph on the right, but basically between 80 and 90% of steel fraction will give, or 95, even 95, will give you a good shielding performance, the rest being water. And you can see also at the back of the shield block a number of cutouts to accommodate many interfaces, such as the manifold, attachment, in vessel coil, etc. This shield block will be attached to vacuum vessel using the blanket module connections. This includes flexible cartridges, which are shown there. It also includes electrical straps to help conduct the current from the blanket to vacuum vessel. And on the top right, you can see a typical prototype of an electrical strap. You also have a number of pads which are used where the keys from vacuum vessel basically interfaces with the keyholes of the shields of the shield block, And you can see on the right also an intermodular pad prototype. Here it has been set up for custom machining. So these different blanket module connections are being procured by Russia. It's very important that we're talking about the shield block and the vacuum vessel and the keys. So the keys on the vacuum vessel are used to react the torque on the shield block. You're going to have, during this disruption, you have high electromagnetic forces generated and moments, and these forces and moments have to be reacted by the keys. And we have to make sure that the load transferred to vacuum vessel is within their acceptable requirements. Vacuum vessel is a safety important class component, and it's very important that we don't exceed the load requirement on the vacuum vessel. And you can see here on the left, typically for a category 3 load or category 2 load, the limit on the vacuum vessel is shown by the pink line for category 3 and by a blue line for category 2. And all our calculations show that under both these categories, either the pink diamonds or the blue circles are below the pink and blue line respectively. Actually, all our components are verified. I mean, we design the components, be it the first wall, the shield block, or others. And in most cases, this verification is done by analysis. So we perform electromagnetic, hydraulic, and thermal analysis first, and then the results are used as an input for the structural analysis and to assess the acceptability of the design with regards to the design code. Here you can see an example of a shield block on the right, thermal analysis, where you can see maximum temperature is about 350 degrees C for the shield block in this case. This is shield block 7. In some cases, we cannot use design analysis because it's too complex. And then we use what we call design validation by experiment, by cyclic testing under specified prototypical conditions of mock-ups representing the geometry in question. In this case, for example, for the joint between the armor, beryllium armor in green and the copper chromium alloy in blue, in pale blue, the joint there needs to be tested or to be validated, if you want, by experiment.